Today's video lesson is about gases and stoichiometry problems, or in other words, grams to moles to grams meets PV equals nRT. For this video lesson, you're going to need both your Unit 3 and Unit 4 notes packets. Grab your Unit 3 notes packet and open it to page 26, and we're going to actually start at the beginning of your Unit 4 notes packet. You should also grab your yellow objective packet, a couple of highlighters, and a pencil or pen for taking some notes. The learning goals for this particular lesson are 10T to give the molar volume of a gas at STP, and 10U to solve stoichiometry problems involving gases. The top of your Unit 4 notes is all about putting the pieces together. We've come to understand that the easiest relationship in the balanced chemical equation is that mole-to-mole relationship. Now we're going to start to incorporate a number of our ideas into stoichiometry. We have a lot of ways of measuring the amount of substance involved in a process and a variety of techniques for turning those measurements into moles. The first thing we learned to use was the mass of a substance. And that was our very basic grams to moles, using the molar mass to find our moles. You've also learned to go from volume of solution to number of moles, using molarity. And we've even played around a little bit with using density to find grams and then molar mass to find moles. Recently, you've learned the ideal gas law, PV equals nRT, and you've also learned about the molar volume of gas, or the idea that 1 mole of gas occupies 22.4 liters at standard temperature and pressure. Today's lesson is going to be about incorporating what we've learned about gases into what we already know about stoichiometry. At the bottom of page 1 of your Unit 4 notes is an example from the solution stoichiometry that we did right before the end of the semester. You're welcome to read through that if you're still struggling with solutions, but we're going to move on to page 2, which deals with gas stoichiometry. We've learned to do basic stoichiometry problems with a general plan of grams to moles to grams. This worked really well when we had the amounts of the two substances measured in grams. You've probably noticed that when we work with gases, the amount of gas is often given in terms of a volume at a particular temperature and pressure. We can get the ideal gas law together with our stoichiometry ideas and begin to solve stoichiometry problems involving gases. At the top of page 2, we've taped in a little patch giving us a new example problem here of gas stoichiometry. In this example, we ask the question, how many liters of oxygen are needed to react completely with 47.53 grams of magnesium if the reaction takes place at 1.25 atmospheres and 35.7 degrees Celsius. We have a balanced chemical equation and a problem. How many liters of oxygen is equivalent to 47.53 grams of magnesium? In the traditional sense, we would have gone grams to moles to grams. And if we jump down to our plan, you can see that that looks very, very similar to what we're used to, with one little twist at the end. For a plan, we're going to go grams of magnesium to moles of oxygen, in the same way that we always have. And then for our last hop, instead of going back to grams of oxygen, we're going to go to liters. And we're going to use our ideal gas law to make that jump from moles of oxygen to liters of oxygen. So now we'll gather our information. The first few pieces are familiar. 1 mole of magnesium is equal to 24.3050 grams of magnesium. That comes from the periodic table. Our second one is that 2 moles of magnesium are going to react with 1 mole of oxygen in this process. That's going to allow us to make the first few steps of our process, grams of magnesium to moles of magnesium, and moles of magnesium to moles of oxygen. Once we get that far, we're going to use PV equals nRT to find out how many liters of oxygen that will be. We know the pressure. We're looking for the volume. The number of moles I don't have yet, but I will have when I make it to the moles of oxygen part of my plan. Our ideal gas constant always stays the same. And we take our Celsius temperature and convert that to Kelvin. Putting these ideas into practice, we start by converting grams of magnesium into moles, and then use the 2-to-1 molar ratio from the balanced chemical equation. I will need 1 mole of oxygen for every 2 moles of magnesium I have. And I find out that to use up all my magnesium, I need 0.9778 moles of oxygen. That's the number that I'm going to need for a number of moles of oxygen. Now I take my information I have about the gas, the pressure. I don't know the volume. I now know the number of moles. I have my ideal gas constant and my Kelvin temperature. And I can figure out that I will need 19.8 liters of oxygen in order to use up all the magnesium. There are a few shortcuts here to stoichiometry problems. For one of them, I want you to look back at your Unit 3 notes on page 26. Page 26 introduced the idea of the molar volume of an ideal gas. The molar volume of an ideal gas is the volume that 1 mole of gas occupies at standard temperature and pressure. It doesn't make any difference what the gas is. 1 mole of any gas at standard temperature and pressure will occupy 22.4 liters. Standard temperature and pressure is exactly 1 atmosphere and 0 degrees Celsius. 22.4 liters is approximately the size box that a basketball would fit inside of. We can use this to give ourselves a shortcut for some stoichiometry problems. Back on page 2 of your Unit 4 notes, we have a situation where we're at STP. We want to know how many liters of hydrogen at STP are needed for the complete reaction of 875 grams of a tungsten oxide compound. It is important in this particular situation that we're operating at standard temperature and pressure. Knowing that will make our lives a little bit easier. Unlike before, when we had to use PV equals nRT, we're going to be able to go directly from moles of hydrogen to liters of hydrogen using the 22.4 liters. So as I build my plan, it's going to look a lot like my plan from before. I'm going to go grams of tungsten oxide to moles of tungsten oxide to moles of hydrogen to liters of hydrogen. But notice this time we don't need our PV equals nRT. We have an easy one-step conversion. Keep in mind, this will only work because we are at STP. So to solve our problem, we're going to go grams of tungsten oxide to moles, use the 3-to-1 ratio from the balanced chemical equation, and instead of using the ideal gas law, we're going to make use of the 22.4 liters of hydrogen being equivalent to a mole of hydrogen. And we find out that we're going to need 254 liters of hydrogen if we're operating at standard temperature and pressure. There is one other, even bigger shortcut that we can use when working with gases in stoichiometry. For a moment, I don't really need you to write anything down. I need you to just kind of watch how a problem like this would take shape. If I want to know how many liters of ammonia can be produced from 5.70 liters of nitrogen and an excess of hydrogen, it seems at first like I don't have enough information to solve this problem. So just for a moment, let's pretend that we are at standard temperature and pressure and do this similarly to what we have done before. If we were at standard temperature and pressure, 1 mole of nitrogen would occupy 22.4 liters. Based on our balanced chemical equation, 2 liters of NH3 will be formed from 1 liter of N2. So we'll use our mole-to-mole equation, our ratio. There's our 2, there's our 1. And then since we're still at standard temperature and pressure, noticing that the nitrogen and the ammonia are both gases, we know that 1 mole of ammonia will also occupy 22.4 liters. So even though we don't have a lot of information, if we pretend that we're at standard temperature and pressure, we find out that we'll be able to produce 11.4 liters of ammonia. Now, it's probably not fair to assume that we're at standard temperature and pressure if the problem doesn't actually say this. So let's look at a different scenario. What if we aren't at standard temperature and pressure? The part of this that depended upon us being at standard temperature and pressure was this part right here, the 22.4 liters and the 22.4 liters again. If we aren't at STP, we can't use that relationship anymore. We don't know how many liters of nitrogen is equivalent to a mole. And so I'm going to leave it just as a question mark for now. We still have that same mole-to-mole ratio, our 1 and our 2 coming from our balanced chemical equation. And when it's time to go from moles of NH3 back to liters, we have the same problem we had over here. We don't know how many liters of NH3 is equivalent to a mole of NH3. But if I look back at the previous example, when we knew how many liters were equivalent to a mole of nitrogen, and we knew how many liters were equivalent to a mole of ammonia, the most significant thing is that these two numbers were both the same. Down here, we don't know what the value of the question mark is, but we do know that because the volume doesn't depend upon the amount or on the type of gas, that whatever this question mark is, that question mark is the same thing. So those two question marks will cancel one another, and it will turn out that we don't actually need to know how many liters are occupied by a mole of the gases. You're going to get the same answer either way, 11.4 liters of NH3. This leads to something that I affectionately call Avogadro's shortcut. The way Avogadro's shortcut works is that if both substances are being used for stoichiometry are gases, and the temperature and pressure do not change during the reaction, the coefficients in the balanced chemical equation can be read as volume relationships. Avogadro's shortcut is at the top of page 3 in your Unit 4 notes packet. So if we look back at what we did, we had this line of stoichiometry, and we decided that from a mathematical standpoint, this question mark liters canceled with that question mark liters, and it wasn't that important that we actually knew what those numbers were. An alternative way of looking at this is to realize that those coefficients in the balanced chemical equation for two gases in a situation where the temperature and pressure don't change, we could actually use the coefficients from the balanced chemical equation as volume relationships. And we can go directly in one step. 5.70 liters of nitrogen. I will get 2 liters of ammonia for every 1 liter of N2 that I have invested, and I come right back to that same answer of 11.4 liters of NH3. So the simplest possible gas stoichiometry situation is the situation represented when both of the substances you're working with are gases, and you have a constant temperature and pressure. Because suddenly, we don't even have to go to moles. We can do so strictly as a volume-to-volume relationship. So we used to say that 1 mole of nitrogen plus 3 moles of hydrogen would yield 2 moles of NH3. It will also be true, because all these substances are gases, that 1 liter of nitrogen plus 3 liters of hydrogen will yield 2 liters of ammonia. And you could even downscale to a much tinier situation. 1 milliliter of nitrogen plus 3 milliliters of hydrogen will yield 2 milliliters of NH3. As you start to apply some of your shortcuts to gas stoichiometry, just remember to be a little bit careful. If you want to use the 22.4 liters per mole, you need to make sure that you have standard temperature and pressure. If you want to use Avogadro's shortcut of using a volume relationship, you need to make sure that both of the substances you're working with are gases, and make sure that the temperature and pressure aren't going to change along the way. So that's how we're going to manage gases in stoichiometry problems. We're going to have to combine our original stoichiometry idea with our ideal gas law, enabling you to now incorporate gases into your stoichiometry problems.